Hi everybody and welcome to the third tutorial, Gauss's law, and now we're going to solve a question about a submarine. Okay, so submarine, how it's look like, let's say we don't need it anymore. Submarine is actually have this strong body, right? Let's do it lower, strong body, right? A wall, maybe let's do some nice propeller here. This one, and also windows, so they can see what's going on inside the sea. Maybe to do here a small Nemo, some fish here, right? Small fish. And also that the submarine have this device to see above the water, right? So this is our submarine, and we're gonna do an axis on the top of the wall. This is the axis. So let's use another one. We have this. This is Z, this is Y, and this is X. Okay? This is my axis, my coordinates. Perfect. Here, we don't need this one, we don't need the negative. And also it's given that the submarine have on the wall a positive charge. Positive charge. And the first question I want to ask you, before we're going to start everything, what is the charge? Let's also say that the charge is 0 equal to P 0 x squared d squared. P0 means it's positive, so positive, and D is how it's the thickness of the wall. Let's do a side view. So here, this is, let's do it in red. This is Z, right? This is X. In your face you have Y. This is you inside the submarine, right? Looking through the window, maybe this is a window, right? To see the fish. Here's the fish. So, and this wall, this is D over 2, and this is D over 2. So the total depth of this wall, the thickness of the wall, is D. Okay? So this is the parameter D. And the first question I want to ask you is, due to the symmetry, that one, using the symmetry of the infinite, I will explain it, infinite wall. This is the wall, and I say it's infinite. I'm gonna explain it soon. Let's underline it. What is the direction of E, which means what is E hat? That's a question. What is the direction of the electric field? Which sense the fish? Okay, so this fish in some distance along the x-axis, and I'm asking what is the direction if I'm telling you that the wall of the submarine is infinite. And let's explain what do I mean by say infinite. I want you to think about a ball. I have here a sponge ball, right? So and it's got a mass, okay? And its mass is finite, some m, I don't know. But this wall is so strong, it's so heavy, this building, the mass of the building is insane. So if in physics 1 you would try to do what is the momentum equation for this collision between this sponge ball through the wall, you would find that it would be really complicated to calculate what is actually the mass of the wall. But you can take an assumption. You can say that the wall is so heavy, the wall is so huge and big, so let's say it's infinite. The mass of the wall is infinite compared to this. Okay? And that's the same idea. What I want to say is that the fish is so small compared to the wall, okay? If we stand next to the wall, he looks up and he see only wall in the z direction, and the minus z, he look down, he see only the wall of the submarine. You look here, you see only the submarine, and you look here, you see only the wall of the submarine. Okay, it's like it's a little bit similar to think about that you in the sea. You're in the sea above some plan. Okay, and you look at the plan and you see in the middle of the ocean, you see only the sea to all the sides, and this is gonna help us understand how the fields acts like. So let's try to give it a shot and actually draw it. Okay, so here it is. So what do I mean by saying that? So I'm gonna change the orientation. So this is my fish, right? It's over here and he's above the wall of the submarine. And I told you, you can go at the z direction. Infinite is always gonna see a wall. The fish is so small compared to the wall. It's like a tiny dot. Here I emphasize just for you to see what is the distances, where the location of each one. And here is the y. And this is infinite. And now let's try to understand what is the electric field direction on this fish. So if I'm gonna take some random z dot here, right? So we thought that it's positive. So when it's come to the fish, boom, I know the electric field is gonna be in this one. But since it's infinite, for each positive z, I'm gonna find the same negative value for z, and it's gonna apply an electric field in this direction. And remember what we did with the b? In the previous tutorial, this is gonna sum up, but the parallel direction to the plane are gonna cancel out. So they sum up, this cancel out, okay, got it. The same thing happened to the z direction, right? Just to turn it around. For each value here, I can find value here and do this same idea. So it's true to the combination of them. If I'm gonna take some dq at the location z and y, I can find here the location, I can find here another one dq with minus z minus y, which is gonna be the opposite, right? So if this is the plan, right? This is the plan. Here, this is the plan, right? So let's do it again, because I think this is really confusing and this is the x direction, right? So if I take this random dot and this random dot, right? So this dot, if the fish is over here, really close to the wall, so we're gonna get this kind of vector, and this one gonna give me this direction vector. This side's gonna cancel out, but this side's gonna sum up. You see it? They're gonna sum up, this is gonna cancel out, sum up, cancel out, sum up, right? Cancel out, sum up, cancel out. So that's the idea. And what is this direction? This direction is actually x. So we know, okay, that the direction of the electric field, we don't know its magnitude, not yet. But we know for sure that if the world is infinite, and for each dq at the z and y, I can find another dq which is gonna cancel all the parallel vectors and give a vertical one, right? Perpendicular one to the plane, right? So let's write it down so it's a bit easier to understand. Okay, so let's write E, right? Direction, let's do vector equal to some magnitude. We don't know what. Let's do it here. We don't know where and what is it, but it's gonna be at the x direction. Okay, y. And you know, the small kid asks why that, why that, why that. So I love this kind of question. Why? For every dq z y, I can find dq minus z minus y, which will cancel the other the direction y and z. They're gonna cancel each other and we're gonna left with that. Another thing I want you to remember what is the magnitude of each one, dE? What is the magnitude dE? dE is actually the distance, let's do it D, the distance from the wall, right? So actually here, I know it's gonna be only a matter of how far I am from the wall, because this is the radial coordinate, right? So I also got a feeling that this is gonna be only dependent on x. So now let's move on to the next question. This is d squared, right? Proportional to the distance from the wall, which is x. X is the distance from the wall. Perfect. So now let's go to the next question, which is we just calculate, right, what is the direction, and now I want us to calculate what is the magnitude. So let's do that. Okay, so the next question, let's do it 2.2. This was 2.1, now 2.2 is actually what is, not 0.3, we in tutorial 3.2 is what is the magnitude? E, we know it's dependent on x, what is magnitude equal to? Okay, let's try to do that. And now we can use Gauss law. Okay, so Gauss's law. So what is Gauss's law? I'm gonna give you a small introduction. I really need the drawing of the wall, so I'm gonna do it here. So Gauss's law actually talking about flux. This is a flux, the electrical flux, and this is equal to sum of many small fluxes, which we're gonna talk about that, and each small flux is equal to this. This is the definition. So the integral, it's the magnitude E multiply the magnitude E multiply by dA multiply by cosinus alpha. And what is it? So to explain it, I need to explain to you what is dA and what is the concept, and here we must have this sign. So in general, let's explain what's Gauss's law. So Gauss's law hold only for closed surfaces. You can think about surfaces, for example, window is a surface, wall is a surface, my face is a surface. But the first thing I want you to understand is a surface can have a direction to point in somewhere. For example, I'm looking to the camera. You know it, the surface of my face looking at your camera. Right now, here there's a window, believe me. So I'm looking at a window. How do you know it? You know it because you see my nose. My nose actually pointing at the direction of the surface. So the same thing I want you to think about this dA. dA presents a small surface, dA, with some nose. This is actually the normal, but I've been lucky and normal start with N and nose start with N. So you can think about its surface as some face that's pointing in some direction. Okay? And Gauss' law is valid only for closed surfaces. Okay, which means, for example, what is a closed surface? Closed surface is something that water cannot spill out of it. That's the way I remember it. For example, if I have a cup of a glass, a mug, the surface of the mug, you know, the inside and the outside is open. Because if there was gonna be water inside a glass, I'm gonna pour it. I can pour it, I can take the water out. But if I have a closed box, this is a closed surface, if water inside, I'm gonna shake it, the water will never come out, right? A bottle is actually a closed surface unless it's open. And you can think about a barrel, you can think about a bowl. This is a closed surface, unless if it's got some window somewhere and water can spill out. So what the idea? The idea of Gauss is to use dA. What is dA? dA is a kind of a puzzle piece, you see? I did like here, puzzle pieces, and dA is actually a vector of the nose, right? So we can do here a funny smile, right? Smile, eyes, and it's hard to see, but this is dA, and with these dAs, I'm gonna build some area, right? I can put here a block of puzzle, here, I can close myself in a sphere, I can close myself in a box, whatever I wanna do, right? And in the end, I need to have a enclosed area, okay? And E is the electric field in this specific dA, okay? This electric field is specific dA, and cosinus alpha is the angle between them, okay? Let's draw it. For example, this is for example, here, some random shape, okay, and it's got some value, and I can split this shape into small puzzle pieces. This is dA, and dA pointing in some direction, and this exists in the world. So there's some electric field in the world in many locations. For example, at this point here, the electric field, electric field, electric field, and also from this point where dA is located, there's some electric field. And alpha is actually the angle between the two of them, okay? This is the idea of what is it, okay? And let's give you some analog. Let's give you some analogy. So you can think about it, that if I have here, for example, this dA, okay, for the angle, if I have here dA, so if there's a rain, flux of rain, not electric field, so I change only E to R, and the rain going down, and so right now, okay, the rain, let's do it here, the rain is going down and dA is pointing down, this specific dA. So what is the cosinus between them? The angle is actually 0, so cosinus equal to 1, so this flux equal to the dA multiplied by E, this specific one. And here on the area, let's say that I did a box, this piece here, this piece here, this piece here, 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 and here, right? So it's a closed box. But let's think about not this part here, the bottom, but some side wall. So right now dA is pointing at me, but the rain still go down. So dA is actually here, E is actually pointing down, so the angle between the arrow and D is actually 90 degrees, which means the cosines is 0, because cosines of 90 degrees is 0. So what we actually want to do, we want to try to use this law to help us. And what's so special about this law? So the law is actually that if you're going to sum all the fluxes, okay, from this small window dA, this must be equal to what? To Q in A over epsilon 0. What this means? It means this must be this summation of the small fluxes on each small window with the electrical field. This sum must be equal to the total charge only, but only inside A, the area you just thought about it. You can choose which area that you want, but only the charge inside A. And you need to divide it by epsilon naught. What this is just a constant, but this is a concept. So I like to think about Gauss's law. G stands for me as geometry. This is the geometry part that we need to do. We need to think about some area, closed area, must be closed area, otherwise it's not working. Some closed area, and it must be equal to the sum of the charging size. So Gauss's S stand for me for sum of the charge. Okay, so sum of the charge inside A must be equal to the geometry. Okay, so how we can think about the area, which area can help me? Usually we want to do two things. We want to have this alpha, you see this alpha, and we want this alpha to be, for example, pi over 2, which means 90 degrees. And what it's going to do to this specific flux, if it's the cosinus have alpha equal to pi over 2, it's going to kill the integral. It's going to kill everything here. So this is really favorable because we love that stuff cancel out and we don't see them in the equations. It's wonderful. It's helped us to deal with the real stuff. Another thing that I want, I really don't like cosines. Okay, so maybe let's do it alpha equal to 0, which means the cosine is going to be 1. So right now I don't need to deal with the cosines. I can deal only with the multiplication of these two. So only the magnitude, the sizes. So this is also good. So usually I'm gonna choose these two for the area, and I want you to have let's go back to the analogy that I gave you before. So remember that I build closed area from this dA as a piece, right? So I did a small box dA, dA, dA. I can even do it larger. I can do dA, 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 dA. I can build like a huge box using this differential area, okay? And it's all gonna sum up to be the total area, which is A. Good, so what I want you to see is, for example, if the rain was going down like this, so you see that here, cosine is gonna get the value 1, because the angle right now gonna be 0. And here it's going up, up, here, until here, what is it? Now it's actually 0, right? It's not 1, now it's 90 degrees. Okay, so this is what I want you to keep in mind. Don't worry about it. I know it's complicated, but this tutorial is all about doing this equation so many times that you're gonna understand the concept. But I really wanted to give you some kind of introduction before I'm gonna dive into how really using it. So now you have a little bit something, not ready, not specifically know what you're gonna do, but let's try to solve some exercises and you're gonna understand part by part what's going on. So, okay, so let's remind you what they ask. They ask, what is the magnitude at a location X? Where is the fish located? Okay, so let's say that the fish is actually distance L, okay, from the wall. Let's try to do it. Okay, I'm gonna clean this up, but I'm gonna write it in a second. So the first thing I need to do, okay, the first thing I need to do is to think about some area. And I am more experienced than you, so I already know what's the area that's gonna help me, but I'm gonna give you tools through the tutorial how to choose area. Each area gonna give you correct answer. The question is if it's gonna be useful, if you can use it to solve the question, not to write something that's correct. So let's use this description. So I'm gonna do a box. Here is a box. See it? So this is gonna be my box, and the box is gonna be actually let's do it symmetrically. This is the box that I decided to choose. The length of the box is gonna be L. Okay. The height of the box is gonna be H, and the width of the box, if it's 3D, right? This is a box. This is 3D. The width of the box is gonna be W. Did everyone understood what is the area that I choose? This area does not exist beside in my imagination. It's not in the wall, but I have some idea for a shape. I need to choose Gauss's geometry. I choose some geometry, not L, let's do it 2L, okay? Because here you see the symmetry, this is L, and this is another L, and here is D over 2, D over 2. It's more convenient to do it that way, okay? Perfect. So let's write the first side of the equation. The flux from this box equal to the integral, and look what I'm doing here. I actually drawing the box, okay? This is thing that I have to do. You don't have to do it, but I think it's helpful. Of the magnitude of each E, right? Multiply by dA, multiply by the cosines between them. This is the first part, okay? Now, I want you to see where is the dA in my question. dA is actually a small piece of area, you see dA, from the box. Can be here, it can be here, it can be here, it's everywhere. It actually like divided the box to small pieces. Okay, that's what I actually did. And this is the dA. And we need to calculate that for each one. You notice this is an integral. If it's an integral, I can actually divide it, right? I can, not divide it, but split it. The sum, the whole equal to the sum of its parts. And if I look at this shape, I can do something really interesting. I can observe this part. You see this part? This part. I have here one here, and here. The end of the box. And I can also think about this part, which is the four sides of the box, right? So I can use my integral, and now it's going to be super useful. I can have this one, right? which is equal to E dA cosines, leave it open, plus, and I have two of those, right? I have one here and the fish, one inside. So it's equal to two of them, plus I have another integral, which is dealing with the long part, long size, right? And I have four of those, right? Why four? Because I have 1, 2, 3, 4. 1, 2, 3, 4, and the other parts it's 1 and 2. This is how I divide the box. Plus. Perfect? This have magnitude E, dA magnitude, right? And cosines. Cosines. And I want you to look at something really interesting. Okay, so we said that the direction of the electric field is always in this direction, right? This is always pointing at the x direction. And what is dA? dA is a nose, right, of the dA. Another thing that I didn't told you yet, that, you know, if this is my face, the nose can go outside and can go inside my body. This is the two options of a surface, right? To go this way or this way. So the convention is like my nose, to go outside, to smell what is outside of the surface, okay? Of the area. The area, you can think about it as my face, my head, closed area, right? So my head is a closed area and the nose pointing outside. So the convention is that the dA, for example here, the arrow of dA should be outside. dA is actually a vector, we didn't talk about it. dA is a vector which have magnitude dA, which is the area, the small area dA, and multiply by this normal direction. This is how you define dA. The one of you that already took fluid mechanics familiar with that, but let's do it slow. So this is dA. And let's continue. So this is dA, perfect. And right now we want to calculate what each one of them equal. For that we need to understand what is the cosines. So if I look to the sides, you see all the dAs pointing in this direction, and here all the dAs pointing, this is at the Z direction, all this, and this is at a Y direction, and down it's the Z direction. So what I see here in this part of the closed area that I choose, the direction can be Z, Y, minus Z, minus Y. This is all the direction of the dA. And X direction is to this, it's here and here, it's X or minus X. This is the electric field. Okay, if I stand here, if I stand here, that's the electric field. So this value actually gonna be pi over 2, because X is perpendicular to each one of these direction of dA, right? So what's happened to this cosines? It's actually dying out. Cosinus kill this flux for each piece. I didn't say that the electric field is equal in every location. I didn't say that. I didn't say anything about these two. But I said that no matter what are the sizes of them, cosinus for each time gonna kill them, because you see we have this angle and we have this angle. This is 90 degrees. The top of the box, the side of the box, the bottom of the box, the other side of the box, right? So it's always gonna die. So we left with this one. Let's try to understand what is the angle. So the angle of this part is X, and dA is also in this direction, right? So the angle between them is 0. And let's go to the other side. Here, it's the negative, right? If this is positive, so the same idea we did before, it's actually to the minus inside the submarine. This is the negative direction of the electric field, and dA also pointing in the negative, so the angle between them is 0. So this cosines is actually equal to 1. Okay, we simplify this. Let's get rid of what does not valid anymore. So we can clean this one and this one. Perfect. Perfect. Okay. So the flux, this is small part of the electrical flux. Actually, of all this area, actually is equal to these two integrals. I put 2 in the beginning. So E, let's think about it. In this location, E is actually equal to EL, right? We said that what really matters is the distance from the wall. That's what's important to the fish. If I'm gonna be really close to the wall, and maybe I'm going to feel a strong electric field. If I'm going to be far away, the distance in the dominator actually going to go down. So this is actually EL. And if this is EL, it's not relevant to the dA. It's the same on every dA. So I can actually pull it outside of the integral. So this is 2E at the location L only. And this is integral of these squares, right? These shapes, dA. And what this integral actually saying, okay, this integral is said sum for me all the area of all the dA that actually sum up to be this part. What is this part? We know its area, it's W, the width, multiplied by H, its height. So this actually is HW. Did you understand? I'm gonna sum all the puzzle pieces, sum them up, until I'm gonna have H and W. That's what's gonna happen. So we got the flux E. Actual equal to 2. These two come because I have this in two sides of this idea. 2 EL. And this is actually L plus minus, right? It's for both sides, it's the same magnitude. EL multiplied by, let's cancel that and write it in the end. EL multiplied by HW. So we found the first part of Gauss's equation. The second part of Gauss's equation is actually calculating what is the other side. We said it's the sum of the charge inside this box. So I cancel this out. Perfect. And let's write it. So here it is. So the other part is Q in A equal to epsilon 0. And this equal to what? To 1 epsilon 0 and sum all the dq, right? That's what we need to find. And this we did in the first tutorial, remember? We calculate many of those. But I want you to notice, okay? This is 1 epsilon 0. This is, we can sum rho, which is the charge density, multiplied by dV, some volume. What is the volume that I'm going to choose? I'm going to choose the x, small boxes of the x, dy, dz, right? This is small boxes of charge. This is the coordinate that I choose. And so let's write that. So it's this idea, right? This is rho. So I actually have here 3 integrals. And here it starts from 0 to h, 0 to w. This was the dy and dz, dy and dz. And here I have also the x. The x is gonna be, and we're gonna talk about the x in a second. And here I need to write this, which is a p0x squared d squared. And now this is a sensitive point. What is the total charge? So I want you to look that this is the wall of the submarine, right? So this is the only charge that we need to take into account. In the water there's no charge, only in the wall, right? Only in the wall of the submarine. So the area is actually, if this is my axis, here's the axis, so it's minus d over 2 till plus d over 2. Got it? This is the dx. This is the distance we need to go. And so you can see this is a constant compared to dy and dz, so I can immediately solve this integral and write in the end this one should be equal to that, so I write here equal to, so this one epsilon 0. Here I have this p go outside, right? This p go outside. This integral gave me hw, so I have here hw. And when I'm solving the integral, I'm getting also 2d24. That's the result of that one. So this one is actually equal to this one. And now I can compare them. That's what Gauss's law said. He said, take care of the geometry, tell me what is the flux is, and this must be equal to the total charge inside the shape, the area that you design, divided by epsilon naught. And when I look at this, I see something really interesting. The 2 and the 2 cancel, and HW cancelled. that means that I could choose other shapes and it was still working, okay? As I told you before, you can choose many cases, many areas as much as you want, but you need to choose one that is helpful. This specific one was helpful. I can tell you ahead that if you would choose cylinder, it was also work on this one, but I want to show you other areas because the next question we're going to deal with cylinders. So what I actually getting, I'm getting that EL, I'm getting that the electric field, let's do it here, I got that E at location L is equal to P0 D24 epsilon 0. That's what I get. And which L we are talking about? We're talking about L's that are bigger than D over 2 or smaller than minus D over 2. That's the concept, that's the idea. And what I want you to notice is that this is a constant. Weird, right? Because think about it, that if I'm close to the wall, like I feel the charge, it's really close to me, but if I'm far away from the wall, like there's a distance, so I would expect it to be, you know, to be smaller when I go out far from the wall, but this is a constant. Why is this happening? The reason it's happened, it's because we said that the wall is infinite. It's true that if I'm gonna be really close to the wall, the electric field is gonna be really high, but if there's infinite wall on top of it, I'm gonna get a lot of contribution from the top and from the down and from this side and this side. So actually, the distance from here to here, it's not gonna be that you know, there's not gonna be a big change. So that's the idea. If you take this assumption, we know that the wall is not infinite, we get to this value. And this is really hold. If I'm gonna think about, for example, the coronavirus, okay? So the coronavirus feels some electric field from a cell, and the coronavirus is really small compared to the cell, you're actually gonna not feel a big change when you're gonna be close to the wall. You're gonna see infinite wall, and the electric charge from the biology cell not gonna change too much. So this is part of the assumption that you take. The real value actually take into account the distance, but if you took this assumption of infinity, the wall is infinity big, this is the result, and that's what you always expect to get when you deal with infinity length. Okay, perfect. So that was really good. Now I want to ask you, what is the electric field if I have here a window, for example? If I have here some window, what is the electric field here inside the window, okay, of the submarine? In the wall, okay, inside the wall. So let's deal with that. I'm gonna wipe this also, so we're gonna have more space. So right now I'm dealing with, let's do it again. So this is the wall of the submarine. This is Z. This is in your face is Y. This is X. And right, I ask you what is the electric field here at this point. Okay, some point inside the wall. So we're gonna do the same technique. So if you didn't understand the previous section, don't worry about it. I'm gonna do it all over again in this one. So I'm gonna do a small box, but this is the 3D box, right? So a small box. I'm gonna do it only from the view of the side, right? But you have a width, and I'm gonna do the integral. So I'm gonna say that the flux equal to the sum of the small fluxes for each window, and each window the flux is actually defined as E dA, the magnitude multiplied by cosines alpha, and I decided that I'm gonna choose a 3D box, but this time the box is smaller than the wall. So right now you see this is 2L, okay, and this is D. You see it? Now it's smaller, okay? And I'm gonna say the same, that I can split this integral into two parts. These parts, which is have H and W, H and W, and you know the sides. I have 2 of those, and I have 4 of those. And for this one, alpha gonna be equal to pi over 2, which gonna kill all the summation. And here alpha gonna be equal to 0, which gonna make this cosinus vanish. Okay, so what I did there, I said that the DAs are the same, pointing in the directions of the wall of the box, right? But the electric field still pointing always to this side, because for each point that I have, I'm gonna find another point. I'm gonna push the electric field to this direction, right? Perfect. So I'm gonna have the same result, nothing changed. So you actually solve in the previous section also this. You also already solved this part. It did not change. So E at L equal multiplied by 2 HW. So this part did not change. The same idea holds also for the box inside. Perfect. So now what we left with, we need to compare this magnitude into the total charge inside. And this is gonna really change. So Q in A over epsilon 0 is equal again to the integral of rho dx, dy, dz integral. And this is the same calculation as before, but this time I want you to look that the x coordinate, I don't gonna go from, remember that last time we did it from d minus d over 2 to d over 2, right? Now I care about only the charge that inside the box, not in other places. It's called Q in A. A is the box, right? So all the plus charge that I have over here does not have anything related to me. It's not hold to the equation. So the only thing that's going to change from the previous is actually I'm going to round from minus L to plus L. That's all. The same charge density, the same limits from 0 to H, from 0 to W, right? The same thing here. But now this, because of the change in the limits of the integral, actually gonna get this equal to 2H W P naught 3 epsilon 0 d square, and this multiplied by L to the third. Okay? And now you can see that 2HW is falling with this idea, and what I have here, actually here EL equal to what? To P equal to P0 divided by 3 epsilon 0 d square L to the third. Now it's changing, because each time I move, I gain more charge inside my closed surface, right? My closed area. Because each time I enlarge the box, it depends on L how much charge there is inside. So this is intuitive, and this holds where? For L's which are inside the box, which mean minus d over 2 plus d over 2. Okay? Perfect. So we found all the electrical field outside the submarine and inside the submarine, inside the wall of the submarine, right? So perfect. Outside the submarine and inside the submarine, it's actually the same. It's a symmetrical problem. Everything is the same. Okay, just add a minus, that's all. So we didn't calculate it for the other side because it's the same. But inside the wall itself, it's this value. So perfect. And we're gonna go to the next question. The next question is actually, I wanna ask you, who knows what's the name of this thing? The thing that helps you see what's going on top of the water line. So the name of this is periscope. Peri is go around and scope is to see, like microscope, to see the micro, right? So periscope or telescope. Tel is far, scope to see what's going on far away. Phone, it reminds me telephone, which tel is far away. Phone is a sound, so something for talking from the big sound. So let's actually draw this part. So right now we have another fish, and the fish is over here. Here's the fish looking at this, and let's do a zoom in to this scenario. Okay, we don't need the submarine anymore. Perfect. So this one, this is this part, here it is, and it's infinite long compared to the fish, which means if you go look upwards, you see only the periscope go to infinite length because the fish is so small, and if you look down, you even don't see the submarine. You see only this periscope. It's so long for the size of the fish. You can think of the fish as a really, really small fish. Okay? And when the fish look at this, here it is. Look at this. We have the direction. This is Z, right? And actually the periscope have a hole inside, right? So the hole have the mirrors, and then you can see when you're inside the submarine, and using the mirrors you can see what's going on outside because the mirror reflect your the light beam, right? So this is Z, this radius is A, and the other radius is B. And I want to ask you, what is the direction of the electric field that apply on the fish? Okay? So let's say use the same analogy that we did before. So the question is E direction, what is it? So if you look at it, so we can think about here, if we can move some delta Z, okay? So this is, I didn't say, but the charge density of this wall is different. Right now it's going to be rho equal to some constant value, okay? It's easy, positive constant value. So if I look at this one, so I can see that I have here direction, and you see where I'm going. This is infinite long, so here I'm gonna have delta Z. So this one gonna give this kind of direction to the electric field. This gonna sum up, and this gonna cancel out. So this is the radial coordinate because this happen in every direction, right? And let's look at from the top. If this is the top, right? This is Y. This is X, here it's Z, right? And we look at some theta, and this is the fish, and the fish is looking here, so no matter in which direction we're gonna do this game, the game gonna be the same, right? It's not different. And also if you think about the angle, so what is the angle do? This is some, I don't know, let's say theta, and this is some theta plus this amount, right? So theta